Okay. Thank you, everybody. Today we'll be having Hadas from Yale talking about Khatam, reducing the communication in multilinear code-based SNARKs. Take it away.
Thank you. Okay, wait, should I just change slides with my?
Yeah,
Okay.
let's just do.
Okay, thanks for coming. I'm introducing Khatam, or reducing communication. Thanks. Multilinear code-based SNARKs. And inspiration of the name is Khatam is a type of inlaid. It's like an art where you inlay wood and metal. It's from Iran, and so the point of this is to make SNARKs smaller. So that is the connection.
You
Okay.
can also minimize the Zoom, like this
Oh, yeah.
attendees list. Yeah.
So,
Awesome.
thank you. Okay, so at a high level, taking a step back, well, as I'm sure you all know, a SNARK is a succinct non-interactive argument of knowledge. And for a long time, SNARKs were mainly built with elliptic curves. However, recently, in the past decade or so, they've been built now with error correcting codes because they're faster a lot of the time, mainly faster, maybe not all the time, but in a lot of cases. Because elliptic curve, if you think about it, each operation uses many finite field or like some number of finite field operations, and in encoding-based SNARKs, you can just use finite fields directly, and the cryptographic assumptions based on its hash or collision-resistant hash functions. And then furthermore, it's post-quantum. So this is the motivation for wanting to build better code-based SNARKs.
Is there a difference in like the sizes of the fields that you consider in the two settings?
Not it's kind of complex. I think different.
In terms
Yes, there is. Yeah, code-based SNARKs can use smaller fields than elliptic curve-based SNARKs, but they still can't use super small fields. Yeah. Good question. Okay, so a lot of schemes in code-based SNARKs are built on FRI, which stands for Fast Reed-Solomon Interactive Oracle Proof of Proximity. It stems from a long history of work in theory based on building PCPs, but this was sort of something that came after and made it PC and used an interactive version of a PCP called an interactive Oracle Proof of Proximity. And it turned out to be highly efficient. And then recently, work that I did with Binyi Chen and Ben Fish, we presented a scheme called BaseFold, which improves upon FRI in two primary ways. One, it translated it to the multilinear setting, which has a series of advantages, which I'll discuss in a second. And then two, we made it things possible over more flexible choice of finite fields. So Reed-Solomon codes can only work over specific finite fields, and that can lead to bottlenecks in some cases. So for example, these are some things, some ways that multilinear schemes can be better. So first of all, in the SNARK, you replace an n-log n FFT with the linear time sum check protocol. Two, replace divisions with multiplications, and multiplications are faster than divisions. And then there's been work from called Binius, which I'll discuss in a second, where they showed that with multilinear polynomials, you can pay per bit of thing you're committing to. So instead of, like, if you want to commit to a bit, you don't have to use a large field element to commit to it. And then finally, you can use the best finite fields for the application. That's related to a different result of BaseFold, not multilinear. Okay, and so just as an example, there have even been follow-up or work since BaseFold was published. And because of the multilinear, because it was ported to multilinear polynomials, for example, STIR is an efficient univariate IOP that managed to reduce the communication complexity. And it was able to get approximately 4x improvement in verifier time by using BaseFold to switch to multilinears. And I think it's primarily because they got rid of quotients. And then Binius had also a follow-up. They were only able to do their trick of committing to bits by using multilinear polynomials that don't use quotients, and using BaseFold, they were able to get a 3x improvement in proof size. And then finally, the flexible field choice means that, for example, if you want to encode signature schemes over a certain finite field, over elliptic curves, you're tied to a specific finite field. Usually you would have to do non-negative field operations, which ultimately has about a 20x overhead, and now you don't. And then also we can use fast finite fields with certain properties. Okay, all that to say that improving BaseFold is a well-motivated thing, but originally BaseFold's proof size was too large for people to want to adapt in practice. It was about 3 times larger than FRI, and that might not seem like a lot, but I guess in blockchain settings and things, size matters a lot. So people cared a lot about that. And so the goal of this work was to improve the proof size of BaseFold. And there's been other people working on this problem in the past year. So, but in the end, these are the two results I think that are most relevant. So one is by Ulrich Hadas, who works at Polygon. He published a result that actually matches the best query complexity of Fry. And this result only works over Reed-Solomon codes, and it has a pretty high error probability. However, the query complexity is concretely the best that we can hope for. So this is used a lot in practice. However, if you care about provable security, it's not so great, because to close the gap of the large probability error, you have to either use proof of work, which has a lot of overhead, or you have to, and has heuristic security, or you have to use a large finite field to basically get that down. And then,
why did you say that the error probability, sorry, but why is the error probability as small as you can hope for?
oh, I said the query
The
complexity.
query complexity.
Yeah, although, okay, but in this work, actually, it was proven in a paper called Deep Fry that in the Fry setting, this query complexity and this error probability is the best you can hope for. I assume it translates to this setting. So I haven't proven that or investigated it, but I assume the result in this paper is like the best you can do for linear codes. Yeah, so anyway, this result extends to all linear codes. It has a very small error probability, and the query complexity, I think, is the best that we can hope for. Okay, and so the key thing into proving this turned out to just be like a fact about linear codes that was unproven. So in Fry, the soundness and that query complexity is proven through a result called correlated agreement. Okay, correlated agreement says that if this pi l and pi r are vectors, so if this combination of vectors, pi l plus r times pi r, if this is close to a code, then the two constituent vectors are also close to the code, and they agree in the same locations. And the idea is that in an interactive oracle proof of proximity, which I'll talk about in a second, we want to test proximity of these two constituent vectors. So we do that by testing a combination of them. But in BaseFold's context and other multilinear PCFs as well, we need to prove something extra, which is that if pi l plus r times pi r is actually equal to that linear combination of code words, then the two constituent vectors are close to the right constituent code words. And the reason we need this is because we want not only a proximity test, but also a random evaluation, which I'll talk about more later. But this was the thing that this paper proves. Okay, so a roadmap for the rest of the talk. First, I will go over prior work and definitions. So I'll define polynomial commitment schemes, show how to get them from linear codes. I will define strong correlated agreement and show that all linear codes satisfy it with the bounds I described. And then I'll touch upon the new soundness proof of BaseFold. Okay, so a polynomial commitment scheme is a special case of a SNARK, or you can think of it that way at least, where a prover commits to a polynomial. At some later point in time, the verifier will send a vector. It's a multilinear polynomial, so it'll send like an evaluation point. And then the prover will send back the evaluation and approve. So the goal of this is like, let's say a verifier wants to evaluate a polynomial, but it doesn't have enough computational resources to do so on its own. So it'll just ask somebody else with more resources and then verify. And the key security property to look out for with polynomial commitment schemes is knowledge soundness, which says that if a prover strategy is accepted with non-negligible probability, then it is possible to efficiently extract a unique polynomial from the commitment. And so the idea behind this is that we don't only have that malicious proofs are accepted, but also that are not accepted. But if anything's accepted, it's also meaningful. So we won't have like an empty proof that can just be accepted, but actually any proof that's accepted, there exists some polynomial time algorithm that with access to the prover could actually extract a thing from it.
The polynomial.
The polynomial, yeah.
Yeah, that was committed to.
That was committed to, yeah. Okay, so in this context, we are building polynomial commitment schemes from error correcting codes by way of interactive oracle proofs of proximity, which I will define next. So in an interactive oracle proof of proximity, our goal is to prove that some vector is close to a code word. And in it, the prover will send an oracle to a vector. A verifier will send back randomness, and they will operate over several rounds. And then the verifier will query the oracles at any locations it wants to, and it will receive back answers. At the end, it either accepts or rejects. If you're familiar with PCP literature, IOPs are like an interactive generalization of them. And most IOPPs use this following primitive, where the prover will send two vectors, pi L and pi R. In reality, it's like one long vector that is made up of these two, but for our purposes, we don't really have to worry about that. So it sends two vectors. The verifier sends a random field element, and then the prover will send another oracle, which is purportedly equal to the combination of those two, pi L plus R times pi R. So the verifier will want to check that. So it will check this consistency at the point J, and it will check that the last oracle pi star is close to the code C. And what we hope is that if pi L plus R times pi R is close to C, then pi L and pi R are both close to code words and they agree at the same locations. So this has been proven, and this is the reason that that IOPP primitive, which is Fry basically that I just showed, is sound.
You said pi plus pi and pi are both are code words, and what was the definition?
Oh, sorry. These are vectors. These are code words.
No.
no.
So you said that if like pi L plus R pi R is a code word, it's close to a code word, then you want that pi L plus pi R, pi L, pi R both are code words.
You want them close to code words. Yeah. So like these are agreement locations.
You also said something else. You also not said something else.
Did I also say something else?
Yeah, so what are the conditions you need?
Yeah. So, oh yeah. This is so there's two conditions for the new work. This is the old results where it's just the one condition.
Okay.
Yeah. Good point. So I'll show that in a second. So this was already proven between 2018 and 2021 in a series of results that shows that if that is close to a code word, then these two are also close to code words in the same locations and yeah. And so at a high level, the soundness of this works as follows. So we know that pi star is delta from pi L plus R times pi R, and pi star is delta from C. By the triangle inequality, that means that the linear combination is close to C, and then by correlated agreement, that means that the two constituent vectors are close to some code words. And originally, the soundness was based on the unique decoding regime, which says that as long as 2 delta is smaller than the unique decoding radius of a code, we're good. Pi L will uniquely decode to some code word, and so will pi R. And that's what we need for knowledge soundness. And yeah, however, this wasn't good enough because it requires 2 delta to be smaller than delta C over 2. So that's a small delta, a large query error, and then you need more verifier queries to.
What's delta C over 2? What's delta C?
Sorry, yeah, that's the good question. That is the Hamming distance, the minimum Hamming distance of that code.
Okay, so
Yeah.
not fractional.
No,
Fractional.
yeah, fractional, relative distance.
Okay. And delta is like the distance that you're checking that the purported random linear the purported linear combination is from the actual linear combination.
Yes, yeah,
Okay.
exactly. Yeah, so we don't want that. So what can we do? Well, our goal, we would like to make delta bigger, because if that distance is bigger, we can query fewer places to get a guarantee about it. However, we're still bound by the triangle inequality. So that means that that guarantee is relaxed now. So we have a relaxed distance guarantee between pi L plus R times pi R and C. And that takes it out of the list decoding radius. Right, so we have 2 issues with this, that not us, this is like old work, sorry, this is prior work. They had 2 issues with this. One is that, but one was fixed by the Johnson bound for list decoding, which says that if 2 vectors are like within a larger, more relaxed radius, there's still only a handful of polynomials that 2 vectors could be close to. But the second issue, which was harder to prove, was that if pi L plus R times pi R is delta far from C, and delta is now the list decoding radius instead of the unique decoding radius, can we still prove correlated agreement? And that was hard to prove. I think they did it in like 3 different results, getting the bounds tighter and tighter each time.
For Reed-Solomon?
For Reed, no, actually not only for Reed-Solomon. I'll show you in the next slide. Yeah, so this is the history of results. Okay, that's the original paper to talk about this problem was RBW 13 in the corner. but then more concrete results were obtained between 2018 and 2021.
So maybe you can move the screen sharing banner.
Oh, yeah, sorry.
Oh, sorry, the green one that's in the middle of the screen.
Oh, yeah.
Maybe you can move the top.
I think it'll go away. I don't know. Okay.
Okay.
So anyway, right, so there were like a series of results starting in 2018. This is what we proved. This is the analogous thing to what we proved in the original BaseFold paper, which is that in delta C over 3, you get this probability bound, and then it was improved over the years. And then eventually in 2021, this one's only for Reed-Solomon codes, and it's what I was talking about. The error probability is worse, but the query error is very good.
So I'm a little bit confused about what's the big math statement.
Oh,
It's
okay,
like
yes.
Math, display math.
This is one way to talk about
Like,
correlated agreement.
Okay.
Right, so
Right.
it's saying that if the distance of the linear combination is greater than delta with negligible probability, so which is to mean that it has high agreement with overwhelming probability
Yeah.
over choice of R, then the number of elements in N for which pi L and pi R agree with the code word
Yeah.
in those same places is greater than this, so we get high correlated agreement. Right, so our goal is that the query error is as small as possible, and so is the probability, and we would hope the probability error also be as small as possible.
So what's this minus epsilon? What's epsilon?
Okay, yeah, so epsilon is a parameter that I haven't talked about yet, but it ends up impacting the probability. Oh yeah, they're connected to each other. What is epsilon? Epsilon's kind of like the loss parameter. Like we don't do things perfectly. We allow for a little bit of loss between rounds, where like a little, like sometimes that linear combination will hold, even though, like, we're trying to prove that the linear combination holds and the two things hold, and we allow for like a little bit of error. Epsilon is kind of an error. Okay, so now going, okay.
Well, there's maybe a question in the chat.
Oh, okay.
Let's see. I can read them. Apologies. Well, I mean, maybe you can. Sorry. Does the triangle inequality give the tightest bound in the unique decoding radius?
No, that's a good question. It does not. There is a tighter bound that we have in BaseFold, but I cannot recall it right now. But we do something a little more involved than just
Okay.
that. It still invokes the triangle inequality though. But using another property of like the type of the IOP, we're able to obtain something better. Well, yeah, we're able to attain delta C over 3. So if you just use triangle inequality, it's delta C over 4. Okay, so now moving to multilinear IOP, which motivates this work. So this is the correlated agreement statement I talked about earlier, but now we also have this second property, as you were asking about, that C is equal to CL plus R times CR. So if that's a code word, we want that to be consistent. And the reason, which I'll describe later, is that we want this to be not only a proximity test, but also a random evaluation test. And if these two things are multilinear polynomials, and C is as well, then this would be a partial evaluation. So I will show that later, but that's the high level idea. Okay, and just to describe the difference between correlated agreement and stronger correlated agreement, because it can get confusing. So regular correlated agreement says this, that if pi L plus R times pi R agrees with C in some locations, then pi L and pi R agree with their code words in some locations, and those locations between pi L and pi R are consistent with each other, but not necessarily consistent with the locations in pi L plus R times pi R. So those might not be consistent. And so we can't guarantee this thing over here. C is equal to CL plus R times CL. Whereas strong correlated agreement, which we'll prove here, they are consistent. And by linearity of the code, then you can prove this statement.
Is there any time that we believe that correlated agreement holds, but strong correlated agreement does not hold?
I think no. We've proven that strong correlated agreement always holds when correlated agreement holds, but it was not known before like a year ago. It was sort of, yeah. I think strong correlated agreement implies correlated agreement. but not.
Yeah.
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 Okay, so now this is the math statement about strong correlated agreement. So one way to write it is the probability that there exists a large set in 1 to n, a large subset, such that the linear combination on that set is consistent with the code word, but the two constituent vectors on that set are not consistent with the code word, is negligible. So these are the range of results, all of which happened in the last year or so. The first one is BaseFold. Oh, sorry, there is actually a mistake in these slides. That should be 1 minus delta C over 3, 1 minus delta C over 2. Apologies. Khatam version 1 was put out in November, which achieved what's often referred to as a double Johnson bound, then updated last month for the 1.5 Johnson bound. GKL24 is another group of researchers that were working on this. And they also got the 1.5 Johnson bound, but with a worse error probability, and then the result from Hadas that I mentioned earlier. So
like, how do we make sense of these results? Like, which of these results is best? Like, if I'm going to reference something, what should I reference? Do these all apply in the same regimes? Do these all apply for, like, I don't know, I guess, like any error correcting code? Like,
yeah, so I just gave these results as like a history lesson. The only ones you would use are this work and HAV24. And those are two different regimes. So HAV24 is Reed-Solomon and with a larger error probability. This work is all linear codes, smaller error probability, but larger error, or smaller error. Is it larger error? So more query complexity on this work than Hadas, but this is more general.
okay,
Yeah, the ACFY24 is work, and that's the list decoding regime, but they gave the result is still in terms of the unique decoding regime, which is interesting. But yeah, this work and HAV24 are the ones that are.
okay. I mean, so by the way, what happens when we sum multiple code words and try to apply strong correlated agreements? Do we just suffer a union bound, or is there something better?
No, it should. Yeah, I think so. I think that holds. I haven't had time to write that up yet, but
The union bound?
yeah,
Yeah.
I think it
it's
holds
cool.
if you
But
do
is there
remember.
something better you can do? Or is-
I don't think so. Or I wouldn't expect so. I don't know why, because this is just that's just like a generalization that generalizes to multiple vectors, right? So I don't think you can do better than that.
Okay.
But I don't know. Maybe I haven't thought about it that much. Okay, so now I'm gonna prove this and sort of a high level. So the overall strategy is to bound a set A, which is dependent on pi L, pi R. And the set A consists of all field elements for which there exists a large set and code words CLCR, such that these two things hold. So the linear combination on S is equal to the linear combination of these two code words, but the two constituent vectors are not equal to any code word on S. And we're going to prove that the size of the set is smaller than or equal to 2 over epsilon squared. So the strategy for doing this will partition A into smaller parts. So we're going to enumerate over all possible code words that are relevant to the set. So basically all code words that are witnessed to some field element in the set. And we're going to union over these smaller sets. So each of these sets, it's like the field elements in A that are specific to that code word. And we are going to sum it up. So the two quantities we need are the size of the list and the maximum possible size of A when confined to just a specific code word pair.
Wait, sorry, I didn't understand what A was.
Yeah, good question. Okay, A is the set of field, basically the set of bad field elements for which the main thing doesn't hold, right? So
Okay.
if you recall, we're trying to prove that.
Okay.
This
As
is
a function
not
of
equal to-
pi L and pi R.
Yeah,
Okay,
exactly.
sounds good.
Yeah, so we're trying to prove that this thing is small.
Okay.
Negligibly small compared to F, the finite field. Okay, so, right, so we're going to prove that this is smaller than 2 over epsilon and this is smaller than 1 over epsilon. Okay, so first we're gonna bound this. So our strategy for bounding this is we're going to enumerate all subsets of 1 to n. And we are going to assign a field element or all the field elements to it for which this holds with respect to the specific code word. So everything here is with respect to the specific code word pair, C1L, C1R. And we will, we want to collect, the goal is to collect all the field elements for which this holds, regardless of what set it's over. And so our strategy for doing that is to enumerate all the sets and see for each set which code words, which field elements is this true for. Okay, so.
Sorry, maybe I'm not super sure that I know what C1, is it C subscript 1L?
Yeah.
C subscript 1R?
Yeah.
So why the subscript of 1?
Because I'm just trying to make the point that these are specific code words. So it's like if you had, if you were to enumerate over all the code word pairs for which that are like witness to a field element in A. So let's go back again. Right, so here we say for all R, there exists a large S and code word at CLCR for which this holds, right? So for every R, there exists a pair of code words. Now what we're doing is we're listing all code words that like make a appearance in that statement, so to speak. Like there's some code words where they'll never be the witness to any R there, like they'll never. But we only want to collect code words that satisfy these locations, these equations. For some
Okay,
R
for
and S.
some large.
Yeah.
Okay,
yeah.
okay. Wait.
Okay, so we're gonna assign field elements to the sets. But it turns out that we never need to worry about assigning two field elements to the same set, because you can just solve this set of linear equations. And if you subtract them, this cancels out. By linearity of the code, you can see that pi r actually agrees with the code word on S1, and that then you can also show that pi l agrees with the code word on S1, and that's a contradiction because we are only considering sets that are bad, so to speak, for which pi l and pi r don't agree with any code word on those sets. Okay, so that's great because now we just have to count the number of disjoint subsets of n. And so epsilon, that's the lost term I was talking about. We only care about sets larger than epsilon. So we know that the maximum size of the set is 1 over epsilon. All right. Yeah. Okay, so good. We've made progress in our proof. Now we just need to prove what the size of L is. Okay, so we're going to split our list of code words into two categories. Either they are a high agreement code word or a low agreement code word. If it is a high agreement code word, then we can use the Johnson bound for list decoding once again, because it turns out the set of code words that are this close to those vectors is polynomial, and this is a subset of that. So we can automatically bound this by 1 over epsilon. So the harder thing to do is to bound the low agreement set of code words. And so the strategy for this is going to be as follows. We're going to build up a set S and a set of low agreement code words. We're going to prove that these two sets are equal in size, and then we're going to bound the sets. Okay, so our goal is to get an S and a code word pair that satisfies this equation for some bad S. And we're going to collect all of them. Okay, so we're going to draw a graph, and we're going to label each vertex with a bad set. And we're going to draw an edge between these two vertices if the intersection of the two sets is greater than 1 minus delta C. Then we want to go through the graph and assign a code word pair to each set that satisfies those equations, and put the set in S and the code word pair in L. Okay, now it turns out by you can prove by linearity of the code that
I kind of missed this step. Like, what is this graph? Where do you,
yeah.
I understand? Like, okay, we want to bound the low agreements, code words.
we're bounding the low agreement. This is a strategy for bounding the low agreement.
So okay.
Yeah, so strategy, we're bounding low agreement. So this is our low agreement box. I'm showing how to build this up, and then we're going to count it.
Okay.
Yeah, thank you. Okay, so it turns out by linearity of the code, we can prove that if 3 sets have a large joint intersection, then they are collinear, which is to say there is a unique pair of code words for which this is true. So the X here is to indicate either 1, 2, or 3. They all have foldings at this unique set of code words. Like there's a unique set of code words that satisfies the 3 foldings. And so because of that, we only, if 3 sets have large joint intersection, we can just assign them 1 code word pair. So we don't need to assign them individual code word pairs because they're using the same code word pair. And by construction, we only added a code word when we added a set, so they're the same size. And then finally, we will prove, we prove in the paper that no three sets in S have large three-way joint intersection. And finally, a generalization of the Johnson bound says that if every three sets in S have small three-way joint intersection, then S is bounded by 1/epsilon.
So why would I think this is related to general, like the Johnson bound?
Oh yeah, I'll go over that in a second. But okay, so this gives us our bound, modulo the Johnson bound part, which I'll talk about now. Okay, so right, so the Johnson bound, one way to state it is that the number of code words that have high agreement with pi is polynomial in the length of pi, right? Okay, and the way that this is proven is you draw a bipartite graph. And on one side, that's called the bottom, the left. Oh, okay, I'll call it the bottom. On the bottom, you put all of your high agreement code words. On the top, you put every element of your vector. And then you draw an edge between a code word and an element if that code word has that element in that position. So C1 gets an edge to the first one if the first element of C1 is that first vector, and so on. And we're gonna look for the number of okay, so we're gonna bound the bottom, the number of code words on the bottom, at a high level as follows. So on one hand, every code word has high agreement. So the degree of every code word must be greater than a certain amount, right? But we have the minimum Hamming distance of our code says that any two of these code words can only agree on at most 1 minus delta locations. So the number of angles, for example, between C1 and C2 is smaller than something, but the degree of each of these is larger than something. And you get this inequality, and when you solve it, you get that the number of code words is smaller than 1/epsilon. That parameter is specific. It's not necessarily, it's actually, it's just it's polynomial in the length of the vector.
So I missed the thing about like, something 3y's intersection has to be small, like why there's few of these like cones.
Yeah, okay, why are there few of these cool? Okay, so C1 and C2 can only agree in at most 1 minus delta locations, 1 minus delta times n locations, because of the minimum distance of the code.
Okay. Wait, so why is that? Because
the minimum distance says that any two code words
right,
disagree in at
Must-
least
okay.
delta C locations, so they must agree in at most 1 minus delta C.
Okay, wait, yeah,
Right.
sorry.
No. Okay, so now we're gonna relate this to sets and subsets to get our initial statement. So you can actually view this, like you can replace the code words as, instead of high agreement code words, we have large subsets of n. And instead of elements of a vector, we have elements of n. And then we draw a edge between S1 and a vertex if S1 contains that vertex. So it's an isomorphic problem. Right, and so before the constraint came that they can only agree in at most 1 minus delta C locations, right? But now the constraint comes that we already declared that they have small pairwise joint intersection. So it's the same situation here. Where, okay, I jumped ahead. It's the same situation here where any two, like S1 and S2, can only have a bounded number of these cones. And so you get the statement that the number of any set, any power set that only contains large sets with small pairwise joint intersection or pairwise intersection is bounded. And then it turns out this generalizes to three-way joint intersection as well. I think it doesn't generalize that much further. Like luckily it generalizes to 3. I think it doesn't even generalize to 4.
Why not? Like just an inequality.
So you end up having to solve zeros of polynomials, and yeah, I think it's yeah.
Like there wouldn't be an explicit form?
Yeah,
Like a closed solution.
yeah, I think so. Or at the very least, it's not. So, okay, so right, so it generalizes to the case of 3. I said that. Okay, here's an example. I gave an industry talk on this, and I didn't give any of the preceding slides. I only gave this slide. So, Right, so just to build intuition about why the number of large sets with small pairwise intersection is bounded. Imagine we have a set of 5 and we want to list subsets of size 3. But now we want to rule out any 2 sets that have intersection larger than or equal to 2. You end up crossing most of them out. You can just go through and verify that. And so that's just to build intuition that this thing is small. Okay, so finally, I'll touch upon how this applies to the soundness of BaseFold. So recall what we want to prove knowledge soundness. Here, we're going to relax it a little bit. Instead of extracting a unique polynomial, we extract a polynomial from a small list. So we can think of it as a list commitment. And we have our primitive again. And now we have strong correlated agreement. So after the verifier checks, we know that pi L is close to a code root CL, pi R is close to a code root CR, and pi star is close to CL plus R times CR.
Sorry, just actually going back to something you said. So, I mean, I understand that if you're doing a polynomial commitment scheme over like the list decoding radius, then there is the possibility of switching to another element in the list. Is that like formalized usually? Like, how do people handle this?
That's a great question. There are techniques for handling this. I think in Word they do this, and then also there's a paper called Redshift where they do this. So essentially there's a compiler from list commitments to unique commitments. In practice, you're still going to be using the unique one, but you can just, there's an easy transformation from list.
You just like to do what, I forget what the test is called, when you pick like a random point.
Yeah, you do that basically. Like, okay, one way to do it would be to interleave it with an extra instance of sumcheck, and then, or like in the commitment phase, have the prover also give a random evaluation, and then every time you test it, you also test based on that random evaluation, for example. So like, you know that, because and then by Schwarzschild, the probability that two. Yeah. Okay, and so then why do we care? So as I said before, we really want this to be not only a proximity test, but also a random evaluation test. So why does a strong correlated agreement give us that? It's because in reality, CL is the encoding of some multilinear polynomial, and so is CR. And so taking the linear combination of them is equivalent to evaluating some larger polynomial partially at R. And then when you do that over several rounds, you get just a random evaluation of a polynomial. And we care about that because you can get, in BaseFold, we get multilinear evaluation by using the sumcheck protocol. So there's a common way to do this. We interleave it with the interactive oracle proof of proximity that I described. And then at the end, in sumcheck, you need to get this random evaluation of a polynomial. That's the last thing you need to do. Once you have that, you've proven your thing. And in our case, you don't need to do an extra step. You just pull from the very last oracle of the IOP, IOPP I described. Thank you. That's everything.
Cool. Yay. Okay, sounds good. Let's go with questions if anybody has any. And then we can go from the chat. There's a couple in the chat that I'll read out. Maybe let's start with the ones in the chat. Okay, so can this be generalized to k-wise instead of 3-wise sets? Does this imply any trade-off or improvement? By George K. I mean, it's sort of we talked about it, but maybe you can expand on that now.
Like k-wise sets in the when I was talking about the intersection between sets.
Yeah, I think so. Maybe you can go back to that slide and George can tell us. Yeah, he says Johnson bound.
Okay, yeah, so I was saying, basically, if you look at this, you end up when you do the inequalities, you get some binomial coefficients, and you do the math out. In the end, you have to find the zeros of a polynomial. So in the case of pairwise intersection, it's just a linear equation. In the case of three-way intersection, it's a quadratic equation. So I think it generalizes, but it might quickly become intractable to solve.
Like, could you like numerically approximate it?
Maybe, yeah.
Which is good enough for us because we just care about what you get when you have concrete parameters.
That's true, yeah.
So do you think that would give an improvement if you tried to just numerically?
Interesting. Oh, because you mean the bound would get better.
I mean, I don't know.
But no, because the linear statement I don't think it'll hold over, but maybe it would. Actually, yeah, maybe I need to think about it more.
Okay,
Possibly you could get an
alright.
improvement that way.
Maybe there's actually something,
Yeah.
that's cool.
Yeah.
I think there was another question. So strong correlated agreement is inherently required for multilinear polynomials compared to univariate, question mark?
Yes. Yeah, and it's actually, I think, required for all multilinear polynomial agreements. I didn't get into it. And I haven't verified it 100%, but I think for like breakdown and for example, that the interleaved type of multilinear polynomial agreements, you also need strong correlated agreement. Because in those cases, you're also asking something of the linear combination. You're not just using that for proximity.
So I actually am not sure why, like, why do you not need strong correlated agreement for univariate?
Oh, right. For univariate, it's just simply because the way it works over Reed-Solomon codes is they're univariate polynomials. And so you can prove evaluation using a different trick with quotients. So because of it's like derived from the fundamental theorem of algebra, you have a univariate polynomial, right? It's like f of x minus x over what is it? F of x minus f of I over x minus I is a degree d minus 1 polynomial if and only if f of x is a degree d polynomial that evaluates to f of I. So
You're
just,
essentially ensuring a strong correlated agreement using quotients.
yeah,
I see.
yeah, essentially. Well, no, not exactly. It's just using a different technique entirely to get binding, I think. But it's just,
Okay.
I guess a high level way to say it is that univariate polynomials are structured in a way that multilinear polynomials are not. So you're able to use facts about univariates in that case.
Yeah, I tried to think a little bit about what quotienting would be like in multilinear or even multivariate polynomials, and it seems like it doesn't.
It's a disaster. I think it does. I think there's a version of it that was in PCP literature, but it's very messy.
Yeah.
Let's see if we had another question. Interesting. So the strong correlated agreement imply that Ligero and breakdown, sorry, these are pretty technical questions, can be extended to the list decoding radius.
I believe so. Yeah.
Yeah. Right. Yeah.
Yeah.
Cool. That would be then maybe you can add that as an additional.
Yeah,
notation,
I had
guess.
plans to, but yeah,
Yeah.
time is so fine.
Yeah. Time is so finite.
But
Okay.
also those schemes are, but yeah, no, I think that would be useful, but they're pretty large, their communications. I don't, but it would be useful for sure.
Yeah. Okay. Any other questions from the members of our in-person crowd? Sounds good. Well,
Awesome.
in
Thank
this
you so
case, let's
much.
make a speaker. Yeah, there's more food if somebody wants some. Cool.
Yes.
Thank you.
This final question
Oh,
from
go ahead.
George.
Oh, wait. No, I think I already
Okay, never mind. Yeah.
addressed that, I think. Yeah.
Yeah. Okay.
Okay.
Thanks. Great talk.
Yay.